When we approximated instantaneous rates of change using average rates of change and tangent line slopes using secant line slopes, we saw that our approximations improved when we took smaller and smaller intervals. When we did this, we were estimating the limit of the rate of change as the length of the interval approached zero. Our overall goal for the beginning of this course is to formalize what we mean by limit, understand the definition of the derivative of a function, and then use limits to find derivatives of functions, which will allow us to directly calculate instantaneous rates of change, including tangent line slopes. Our first step is to understand intuitively what a limit is so that we can then formalize a definition. When we looked at the example of an object whose height above the ground in feet after t seconds was given by the function f of t equals negative 16t squared plus 20t plus 400, we estimated the instantaneous velocity at 3 seconds by calculating a few different average velocities over shorter and shorter intervals. We called the function h of t, but I'm changing it to f of t here to avoid confusion later. To remind you of that example, these are the values that we calculated. The rate of change from t equals 3 seconds to t equals 3.1 seconds was f of 3.1 minus f of 3 over 3.1 seconds minus 3 seconds, which was 308.24 feet minus 316 feet over 3.1 seconds minus 3 seconds, which was negative 7.76 feet over 0.1 seconds, or negative 77.6 feet per second. A similar calculation showed that the rate of change from 3 seconds to 3.01 seconds was negative 76.16 feet per second, and that the rate of change from 3 seconds to 3.001 seconds was negative 76.016 feet per second. We also showed in the example after that we could derive a formula for the average velocity at 3 seconds by evaluating the average rate of change from t equals 3 seconds to t equals 3 plus h seconds. And we got that f of 3 plus h minus f of 3 over 3 plus h minus 3 equaled negative 16h squared minus 76h all over h. We did end up canceling an h from the top and bottom, but I'm deliberately not doing that now to make a point later. So let's think about what we did in a different way. What if we had started by determining the average rate of change for the interval t equals 3 to t equals 3 plus h was given by the function r of h equals negative 16h squared minus 76h over h. The way that this function works is you input the length of the interval h, and it outputs the average rate of change r over that interval. Then we could ask ourselves, what happens to the rate r as the interval length h approaches 0? And we could attempt to answer that question by plugging in values for h. If we mirror what we did originally, we could calculate that if h equals 0.1, r of 0.1 would be negative 16 times 0.1 squared minus 76 times 0.1 over 0.1, which equals negative 77.6. This is the rate of change from t equals 3 seconds to t equals 3.1 seconds. If h equals 0.01, then r of 0.01 equals negative 16 times 0.01 squared minus 76 times 0.01 over 0.01, which is negative 76.16, the rate of change from t equals 3 to t equals 3.01 seconds. And if h equals 0.001, we do the same thing and we get negative 76.016, the rate of change from 3 seconds to 3.001 seconds. Just by looking at these numbers, we can see that r at least appears to be approaching negative 76 as h approaches 0. It's also important to realize that the idea of calculating the average rate of change breaks down if we actually let h equal 0. If h equals 0, then r of 0 equals 0 divided by 0. What is 0 divided by 0? Well, we know dividing by 0 isn't allowed. But another way to think of it would be, what number do you multiply 0 by to get 0? And the answer is anything. So we will refer to 0 divided by 0 later as an indeterminate form, because you can't tell what's going on just by looking at it. Basically, what is happening here is we're trying to calculate the slope of a line through 2 points, but we actually only have 1 point. So of course we can't get a slope. Why is this important to notice? When we talk about limits, we are only ever talking about letting something approach something else. It never actually gets there. So as long as we let h approach 0, but never quite equal 0, we will always have 2 distinct points, so we can calculate a slope. An intuitive understanding of what a limit of a function is would be that the limit of a function, g of x, as x approaches some value a, is the value that the outputs of g approach as x gets closer and closer to a without actually equaling a. This is not nearly precise enough for mathematics, and we will formalize it more later, but for now, this is a good working idea of what a limit is, and it will allow us to look at some simple examples.